Okay. So yeah, today's talk will not be about CMEs and ICMEs, but about solar wind and heliosphere. There's many talks about solar topics. One starts with the Carrington event, which is a very well-known one, but this will be actually the only part where we go a bit closer to the sun. The rest we will focus on the heliosphere and on the solar wind. But first I wanted to say a few words about how we learned about all these things. So the Carrington event, for those of you who don't know it, is a very famous case that happened in 1859 when he was making a sunspot drawing here, well, actually in the UK. And he saw at the same time that he was drawing the sunspot that there were some bright features moving in the image. He didn't know at the time, but that was a solar flare that he was observing. Actually quite a strong one that was related to a CME that arrived to the Earth a few hours later, almost one day later, and created a very large geomagnetic storm. So the important thing to record here is that this was probably the first or one of the first cases where one could link something happening at the sun with something else happening at the Earth sometime after. So it gave us some idea that there is an influence, direct influence. This was also observed by another astronomer, but this is just some observation. And soon after that, in the early 1900s, there were several scientists that started to think or to suggest that there was something flowing out of the sun continuously. And they said that the Earth is being continuously bombarded by rays of electric corpuscles emitted by the sun. This was, of course, not proven. It was simply a theory by then. A few years later, in the 30s, there were some scientists that calculated that because of the way we see the solar corona during eclipses, the temperature there must be very high because it is, they see it as it expands into space. These were some observations from that eclipse in the 1930 from the US, so we have some photo here. There was also something, this is something I found it funny, there were, these people went on a plane and took a video of the eclipse, and they call it talking movie because they were recording the time at which they were making the images, so then they had this kind of vocal timestamp for analyzing the images after. More or less at the same time, also in the 30s, with the creation of the coronagraph by View, it was possible to calculate a bit better that the temperature up there in the solar corona must be around that value there, 600,000 K, he calculated. This was not accepted very easily by his co-workers. Took a time to make them believe this. And it was actually by spectroscopy that this could be proven later, and by that also they could get rid, let's say, of some element that they have invented. It was called coronium. But then when it was accepted that the temperatures at the solar corona were this high, it was easier to explain this emission from this element as being an emission from highly ionized iron. So you don't need to invent a new element when you have those high temperatures that will, what you are seeing is highly ionized iron. That was not believed to be an explanation before that, before we knew that the temperature there was so high. Also then there was Chapman soon after that he said that if the gas there is so hot, then it will be a very good conductor of heat, and the atmosphere or the solar corona must extend into space. There were many things going on, observations and theories around 1930 and 1950. In parallel to the theories, it was several observations by a German scientist, Ludwig Biermann, who noticed that by observing comets, he noticed that there is always a tail that is pointing away from the sun, independently of the movement of the comet. So he postulated there that there must be something coming out of the sun, which is pushing this tail away from it. And he made some pretty good assumptions, saying that this gas must be something that is flowing out from the sun with speeds between 500 and 1,500 kilometers per second, which is quite good estimation actually. I think I have this. There was actually a series of papers. This is the last one, I think, where he says several things that looked interesting. So here he suggests already the existence of the solar wind. He doesn't call it solar wind. He has two previous papers which speak about this. I think the first one was in 52, and this is the third one in 57. And there are many things. It's a very short letter. It's actually 2 pages. I think I put some more extracts of it. Here he talks about the density of the outflow from the sun. Actually, it comes from previous studies where they claim that it should be for the quiet solar wind of this in terms of 10 to the 2 per cubic centimeters, or 10 to the 5 when there is a geomagnetic storm. These values are quite high. Here he was a couple of orders of magnitudes too high, but still anyway quite respectful, I would say. And then this is all from the same paper, from the one in 57. He was already talking about co-rotating atmosphere, a 1,000,000-degree solar corona. And I found it also interesting that even though he had all these very well or very good assumptions or theories, his conclusion was quite vague, as we many times do in our papers, even when we know that he claimed that we need new observations and better way to prove this. And actually, shortly after that, it was an American scientist, Eugene Parker, that kind of got all these pieces of the puzzle that were lying around, and he put them all together, and he said that the Chapman models of the expanding corona should be related with the observations of the comet tails by Biermann. And then he wrote the famous paper in 1958, where he explained how the solar wind, he also didn't call it solar wind by then, it came a few years later, could flow away from the corona, and he explained why. So it's because it's so hot that they will fly away even beyond gravity. This is again one extract from the paper where he says that if the conclusions of Biermann of the previous paper that we saw are correct, then we should have a continuous stream of ionized gas that carry away with it the solar magnetic field into space. I think I have put also some other. Yeah, so he claims, there are claims about solar wind speed. All this is, of course, before any measurement of the solar wind. He says that if this is to be true, then we should review the mechanisms of coronal heating, and he says he will do that in a following paper. It took actually quite more than one paper in order to establish that, but there is I will not talk about coronal heating because there is a similar plan, I think the next one about that. So he was already also talking about the 1,000,000-degree corona, and he's all the time, as you saw, he's citing Biermann. So he calls the outflowing gas suggested by him, and he mentions him many times in the paper. So at least here at the beginning, there is no mention of solar wind or Parker solar wind or so on. It's more like Biermann outflowing gas. He also postulated that this the solar wind that carries out the interplanetary magnetic field should decrease by the 1 over r squared with distance from the sun, which it's already been proven by many missions. We will see that. This was the solution that he found for the solar wind. So here in this axis you have speed, and this is distance from the sun. So there are many possible solutions to his equations of a corona such a temperature, and actually the one that is feasible is number 5, as you see it here, because it's the only one that starts with low speed close to the sun and flies away into space farther on. All the others are cannot be used to explain the solar wind. This curve or these observations and these calculations were proven to be right later by many missions. So here the first one was in 1960. And what goes here beyond the critical point is actually the Alfvén radius. So when we below this point, everything is dominated by the magnetic field. After that, the solar wind can flow away from the sun. And he predicted also, or he showed in his papers that the solar wind will flow radially away from the sun, but as the sun rotates, the magnetic field will have this kind of Archimedean spiral shape. And well, his paper, the very famous one, in 1958, was rejected. It was not very well received, and it was thanks to the editor who believed in him and pushed it forward that it could finally be published. And so 2 years later only, the theory was confirmed through the first direct observations of the solar wind. And then we had a theory to explain what had been observed already for over a century about the solar activity influencing the Earth, and what is the cause and what is the consequence of each process. There is an updated figure of that solution, where we have the solar wind speed and the distance from the sun, and we see here the solar wind curve, and it shows also interesting stuff like the position of the Earth and Mars, and the missions that have or that will explore this region of the heliosphere. So we had previous explorations here. I will use this. This was the Helios mission that went up to 60 solar radii from the sun and could sample the solar wind in situ. This was in the 70s and in the 80s. Solar Orbiter will go a bit farther when it's launched, and there is Solar Probe Plus or Parker Probe Plus that will come very, very close to the sun and will, of course, provide further confirmation of all these calculations. We have already had, as I said, several confirmations. This again, speed versus distance, and the plots that you see here are blobs or things flying out from the sun, which were measured by SOHO, by LASCO, by a coronagraph. And if you put them here and then you fit this line here, you can compare with the different solutions of Parker. This is the varying temperature of the solar wind. So if you see for the 1 million degree Kelvin, is more or less similar to this one. And if you extend this a bit more, you get to 60 solar radii, where this was observed there by Helios. So here there is almost 30 years difference, but you can see that this curve can be very well reproduced with modern observations. And of course, we can see now the solar wind with coronagraphs. This one should have started. With heliospheric imagers also, where we see this continuous outflow of particles from the sun. Also, there are some coronal mass ejections there. Then we can also study it as the solar wind arrives in situ to a spacecraft. What I'm showing here is some, sorry, I was a bit sick, so I'm still, it's some results from Ulysses. Ulysses was a very interesting mission because it went very high in latitude, up to 80 degrees south and north, so it could observe the solar wind coming from the polar coronal holes on the sun. And these are some of the results. For the first orbit, it was happening during solar minimum. So we see what you have here is the sunspot cycle. So we see that for the first orbit is solar minimum, and what is plotted here is the solar wind speed. So when we are at low latitudes, let's say up to 30 degrees in latitude, we see the slow solar wind that is coming from the streamers and from the closed loops regions. When we go beyond around 30 or 40 degrees in latitude, we are seeing the fast solar wind. So here this is 400, this is about 700-800. And we see, or we know, that there are these two types of solar wind, the fast one coming from the coronal holes, the slow one coming from the streamers. The color represents the polarity of the field, so red is outward and blue is inward pointing magnetic field with respect to the sun. So we could see the clear structural division in latitude of the two types of solar wind. This is during solar minimum. During solar maximum, that was during the second orbit of Ulysses, the situation was very different. because here we don't have the corona structure as it is here. You have coronal holes at every latitude, not only at the pole, and you have the sources of the slow solar wind are also located at any latitude. So the speed of your solar wind is now no longer divided into fast and slow solar wind by latitude, but you have a continuous alternation of the two types of flow. The third orbit was also during solar minimum, or coming to solar minimum. So these are some of the parameters of the slow and fast solar wind. It's not only the speed that is different, but many other things like composition or source or their signatures that will vary depending on the type. The third type of solar wind could be called the transient solar wind, coming from CMEs, for example, but this will not, it's not a regular thing, so we don't deal with it here. Also, the way we see it at the Earth is normally, at least here when we do our space weather forecast, we use data from ACE or now from Discovery, but it looks quite similar when it works. And I wanted to put this plot because here we have the two types of solar wind in one plot. So you see here, I think the battery of this one is dying. This is the speed here, and we see the first part of the plot. We had low speed below 400 kilometers per second, and then in the second part we have speeds of about 700 kilometers per second. This is 2 days more or less of data. So in that time we can, the situation can change. And we see other things here like the magnetic field intensity in white, the angles of the magnetic field vector, and the temperature here in green. What is important to see also is that when the fast solar wind coming from a coronal hole is running into the slow solar wind that is in front because the sun is rotating, we have the formation of this interaction region between the slow and the fast solar wind, and you can notice that the magnetic field can go quite high because this is a region where the solar wind is compressed. So these high intensities of magnetic field could also result in geomagnetic storms. I think there is a plot now. They are so-called correlated interaction region. So we have a region of a high-speed solar wind from the sun, which is pushing into the ambient slow solar wind, and it's creating a region which with compressed solar wind. And the important thing, apart from compressing the plasma, is also compressing the magnetic field. So these structures can also be geoeffective, and they are important for, as we will see, for other things out in the heliosphere. And these are called CIRs, or correlated interaction regions. As Parker had predicted, we can see here how the intensity of the magnetic field varies with distance from the sun. So this is the magnetic field intensity, and in black here you have the distance from the sun in AUs, in astronomical units. In red is the latitude, because this is measured by Ulysses. Ulysses, apart from going up to 80 degrees southern and northern latitude, it went up to 5 AU, so we could measure the solar wind from the Earth up to 5 AU. And we see that when R is low, the magnetic field is high, and the opposite. So this is the variation with radial distance of the magnetic field. We also see how the corona relates to the solar wind in this plot. We see this is 96, 97, 98, and 99. So this is solar minimum here, and this is almost solar maximum here. You can see how the corona varies from being very homogeneous to more chaotic when it's close to solar maximum. And this is reflected in the solar wind that we measured. Here is the latitude. So when Ulysses was at high latitude, we were measuring a quite stationary fast solar wind. Then when it started going low in latitude, what you see is a constant up and down of the speed, because you are seeing the influence of some coronal holes. And then when it gets to low latitudes, you only see the slow solar wind, unless you are entering into solar maximum, and then the situation starts to change again, because you are starting to have coronal holes at all latitudes that can produce the fast solar wind. Not only the two types, we can look at the corona and at the in situ solar wind and compare the types of solar wind, but we can also see that the different structures that we see in the corona are somehow reflected in the solar wind pattern, especially when we go close to the sun. You cannot see it here, but this was at about 60 solar radius, so about 1/3 of the distance between the Sun and the Earth, measured by Helios when close there. So we can capture also the fluctuations in the solar wind that represent what we see in the corona. So at the Earth, the solar wind is responsible of many things. So it shapes the magnetosphere, and it produces, represents our connection with the Sun, and it manages, let's say, the space weather that we see at the Earth. We have, as I was saying, the prediction or the calculation that they had done in the 50s of about 100 particles per cubic centimeter was a bit high. It's about 5. The composition is mostly protons with some 4% of helium and smaller fraction of heavier ions. And here you have again a table with some of the characteristics of the solar wind at 1 AU. But this is for the slow solar wind at 1 AU, because what happens is that, as I showed you before, we not only have slow solar wind at 1 AU, we also have fast solar wind, and this is even at solar minimum. This is because the polar coronal holes, which are marked here as gray areas, they have low latitudinal extensions that you can see here, and then because of the different orientation of the solar rotation axis and this is the Earth here, the orientation of the Earth axis, we are not only seeing what comes from the 0 latitude at the Sun, but we see also things that happen at higher latitude. We also get them at the Earth. And here we can also see how one hemisphere of the Sun has positive magnetic field polarity, so magnetic field pointing away from the Sun, and the other one has negative. And when we go through these structures, we see the so-called sector boundary structures in the solar wind, where we change from one polarity to the other. And then going even more 3D, we get to the heliosphere. Actually, the heliosphere is the region that is filled up by the solar wind. This is a very easy or straightforward expansion. Let's say if we have the Archimedean spiral and then we go up to higher latitudes. We will talk about the different boundaries of the heliosphere very soon. Yeah, it's here. I think there is even a video that I have put here to show how the solar wind fills up the heliosphere. It goes well beyond the orbits of the solar system planets, and it forms the heliosphere, which is in turn being modified, or in the same way that the magnetosphere is influenced by the solar wind, the heliosphere is influenced by the interstellar medium that gives also its shape. There is a heliotail, so it could be, there are many similarities with the Earth magnetosphere. But also to know which part of the magnetosphere, of the heliosphere we are, or if we had crossed any of its boundaries, one of the things that is used is the energetic particles, so cosmic rays. We can distinguish basically two origins. We can have particles accelerated at the Sun or at processes that come from the Sun, like CMEs or correlated interaction regions, because these two things can drive shocks, and shocks can accelerate particles. And we can also have galactic cosmic rays, so coming from outside of the heliosphere, and we can recognize one or the other based on their energies, their anisotropies, their composition. So these are tools that are used currently to say which and which part of the heliosphere we are in, as I will show later, for example, with the Voyager spacecraft. And we know that the galactic cosmic rays are modulated by the solar cycle, by solar activity. So we see that in the years of maximum activity, around 2000, we have a minimum of the galactic cosmic ray influx that goes to maximum during solar cycle minima. And in this plot, you see the modulation that happened in the last solar minimum. So it's the red curve here. This is the solar minimum in 2009. That was we had more galactic cosmic rays penetrating into the heliosphere, because this minimum was very weak or very strong. I mean, there was a very marked minimum. And this works, the modulation of galactic cosmic rays, by shielding from the sun. So all the CIRs and CMEs which are being created at the sun, this is an animation that shows for this time here, all the CMEs that are coming from the sun. This is done by in the haircuts project. So we can see that all this material and magnetic field which is being expelled from the sun, together with the correlated interaction regions which are not here, they need to go somewhere. And actually they fill up the heliosphere and they help in shielding from galactic cosmic rays. And that's why the cosmic rays have a peak during solar minima, because you have much less of all these things which are shielding us. And there is one more component, so it's like a mixed component of the cosmic rays, which are called anomalous cosmic rays, and they start by neutrons coming from the interstellar medium, which are then ionized in the inner heliosphere, and they are taken up by the solar wind, because before they were not affected by the magnetic field because they were not charged. They are taken up to the termination shock of the heliosphere, where they are accelerated there, and they come back in the heliosphere as energetic cosmic rays. Oh, actually, I think I have the explanation here. Yeah. And these are called the anomalous cosmic rays. And as I said, okay, there is something also that was observed by Ulysses when going to high latitudes. What you see here, this is speed and energetic particle intensity. This is solar energetic particles. And it was believed, or it was supposed, that when you are at very high latitudes, as you see here, the speed is 700 to 800 kilometers per second. So Ulysses was above the poles of the sun, the northern solar, the northern polar coronal hole of the sun. And here you are not expected to observe energetic particles like what happened in this region here, but there was quite an amount of time, these are years, where the flux of energetic particles was still observed at these very high latitudes. And there was some confusion as to how this can happen, because energetic particles need to be accelerated by shocks or by flares, the ones coming from the sun, which you don't see at the poles of the sun. So there must be a way to explain how these particles can get up there. And this was done by finding a new model for the interplanetary magnetic field. This is the classical picture, the one from Parker, where we have the Archimedean spirals going up in latitude, and we have the magnetic field at different latitudes. But if we take this picture and we add some ingredients, for example, that the solar rotation axis is not parallel with the dipole axis, and the photosphere is rotating differentially in latitude, then what you have is that the field lines, instead of being like this when you go up in latitude, they are a bit more random, and there is certain level of interaction between the field lines at low latitudes and the one at high latitudes. So this is the model by Fisk in '96. And some of these high energy particles that we observe at high latitudes could be explained by this phenomenon, or by this new model. And as I said, to talk a little bit about where the heliosphere ends, we have here the sun, the planets. All this is being filled up by the solar wind. There is something called the termination shock, which is actually when the solar wind goes to subalbenic speeds, and it can no longer follow or be connected to the sun. Actually, there is one more. Yeah, this drawing is actually, I find it nice, because you see here inside the termination shock, you have the normal picture of the solar wind as more or less as in a Parker spiral. But there is some point where the solar wind speed, that is decreasing a bit with distance, goes so low that it cannot really keep track with this, and it's simply flowing into the heliospheric tail. So this region where this happens is called the termination shock. And what comes after is the heliosheath, which finishes in the so-called heliopause. Sorry that this is in German, but I like the drawing. At the heliopause here, we have a difference. Up to here, we are still talking about solar plasma. After the heliosphere, after the heliopause, what we have is plasma coming from the interstellar medium. So these are the divisions that we know. So the heliopause between the interstellar medium and the heliosheath, and the termination shock between the heliosheath and the inner heliosphere. And we know a lot or a little, or it depends, but we know things about all these boundaries, first from theories, of course, but also from the Voyager mission. This is a poster that was done last year when the Voyager mission was 40 years old, since it was launched in 1977. And there are two spacecraft, they are still going on. And there is one, this is a bit small, sorry. If you go to if you are interested in seeing more detail, in their website, actually, they have quite a nice app where you can plot, you can see the location of the two Voyagers. This blue shady thing here is the heliosphere. Here we see that Voyager 2 is still inside the heliosphere. It hasn't passed the heliopause, which would be this limit, but Voyager 1 is already beyond that. And here you can, in the app, you can choose the date. You can even see the real-time measurements done by the instruments. I think I put something here. Yeah, this is from 2012, when Voyager 1 went into interstellar space. And what you see here is the fluxes of solar particles and the fluxes of external particles. So this change from within the heliosphere to outside the heliosphere, if you play, I didn't put it here, but you can play a movie, and you see how the green line is very high, and then as you go through the heliopause, the orange lines of particles coming from galactic origin are much more dominant than the ones seen from the sun. Yeah, this is a status now, well, last week, where we can see, so this for the Voyager 1 is what I just shown you, so there are very few particles coming from the solar system, everything is coming from galactic origin, and in Voyager 2 is the opposite, so it's still inside within the heliopause, so we have more particles of solar origin than of interstellar origin. The one is at 141 AU from the sun, the 2 is at 117, and this one is believed to be already in interplanetary space, and they have energy to run for at least 2 or 3 more years, so maybe Voyager 2 will also make it outside of the heliosphere. Here are some observations. This is when Voyager 1 in 2004 crossed the termination shock. We see this is the magnetic field. Actually, in Voyager 1, the plasma instrument is working. No, sorry, the magnetic field instrument is working. That's why we see this, but not the plasma instrument. The plasma instrument broke down, but it is working in Voyager 2, so we will see it there. And here you see the increase in galactic cosmic rays particles as we cross this boundary here. We get more and more particles from outside the heliosphere. This was, let me see. So it crossed in 2004 when it was at 94 AU. Voyager 2 also crossed the termination shock, but not the heliopause, so it's inside the heliosheath. And here we see the plasma instrument in Voyager 2, which is working. We see the drop in speeds, so from kind of normal solar wind values around 400, dropped to about 100 when after it passed beyond the termination shock. And this is the latest observation, the last, let's say, there was some controversy about this. This is when Voyager 1 in 2012 is supposed to have crossed from the heliosheath to the interstellar medium. And as you can see here, there are some question marks and there are many doubts, but especially people are surprised that the magnetic field is so radial. This is the angles of the magnetic field. You see the values here. So at the Earth, we normally measure 5, 10 nanoteslas, even 20 or 30 when we have CME. Here we are talking about 10 orders, so 10 times less. So this very, very small magnetic fields. And the proof is not only, people believe that we are now in the interstellar field because, first because of all the structure that we're seeing crossing here, because of the particles which are coming mostly from cosmic origin, but also because of some simulations that one could do with the plasma characteristics. So here, this is temperature, this is density, and if Voyager 1 is outside the heliosphere here, it should be seeing a much lower temperature and denser plasma. And this is proven, or there are some observations from plasma waves where you can then determine density, for example, and this seems to also to agree with this situation when Voyager 1 is outside the heliosphere. Voyager 2 is still inside, and since the 2 has still the plasma instrument working, it should provide a final confirmation if the energy lasts until it crosses the heliopause. I think that's all I had to say. Yeah, there is some summary, very general summary, but that was all. Thank you very much.